let's find the area under y equals x cubed on the interval from 1 to 2. And I've gone and graphed the function and shaded in the area we're finding. And right now, our only tool to find this area is to write down a Riemann sum, find a formula on the number of rectangles, and take a limit as n approaches infinity. In section 5.4, we'll have a more convenient way of finding this area, but it's important to always be able to go back to this definition of area where we're actually finding a finite sum and then taking a limit as n goes off to infinity. I know my Riemann sum will have the format as a sum from 1 to n of f of ck and times delta x. I'm going to let the ck be the right-hand endpoints, just as we've done in the previous videos, and delta x will be b minus a all over n. My right-hand endpoints are actually interesting here because a is 1, and then k times delta x. So my right-hand endpoints will always be 1 plus k over n. So that's the value I actually have to plug into my function. So I'll need to cube 1 plus k over n, and then multiply it by 1 over n, that value of delta x. Well, you can multiply this out many different ways. You can actually just take some scratch paper and write 1 plus k over n next to itself 3 times and distribute. I always like to think about Pascal's triangle. But any way you do it, you end up with 1 plus 3k over n plus 3k squared over n squared plus k cubed over n cubed times 1 over n. Now I need to distribute that through. So then I have a 3k over n squared plus 3k squared over n cubed plus k cubed over n to the 4th. And so now I need to rewrite this as the sum of 1, 2, 3, 4 different sums. And I can see I'll have some constants I can go on and pull out front. I think I'm going to go on and do all of that in one step. Just pulling the constants out front and rewriting this as the sum and difference of sums. And what I see is that I now have sums that I have rules for. In fact, this first part, the sum from 1 to n, the sum from 1 to n of 1 over n would just be 1. That would be n times 1 over n, I'll get 1. Plus 3 over n squared times, and I have the sum from 1 to n of the first n whole numbers, just k. And I know that's n times n plus 1 all over 2. Plus 3 over n cubed times the sum of the first n squares is n times n plus 1 times 2n plus 1 all over 6 plus 1 over n to the 4th times, and then the sum of the first n cubes is n times n plus 1 all over 2 squared. And so I'm able to use everything I know about sums, and I have this very long formula in terms of the variable n. And we could simplify this and we could get it kind of in the simplest form, but I'm only trying to take a limit as n approaches infinity of that statement. And so I'm not even going to worry about simplifying it. I'm just going to write everything down and see if I can take the limit of each one of these rational functions as n runs off to infinity. All right, so there's my limit. If I can evaluate that limit, I'll have my area. Well, as n goes to infinity, 1 goes to 1. That part's not too bad. On top, if I multiply that out, I'd see a 3n squared. On the bottom, I have a 2n squared. Degree is the same on the top and the bottom. That's going to 3 over 2. If I multiply this one out, on the bottom I definitely have a 6n cubed. And if I multiply the top out, the highest degreed term would be 6n cubed. So as n goes to infinity, that term's going to 1. And just one more to go. Multiply the top out, I have an n squared plus n on top, but the highest degree would be n squared. On the bottom I'd have 2, but I need to square it. And so when I do that, that would become an n to the 4th on top and a 4 on the bottom. So on the top I have a 1 times n to the 4th, but on the bottom I have a 4 times n to the 4th. And that would be a plus 1/4. And so I need to add these values together, and that should give me my true area. So let's see, 1 plus 3 over 2 plus 1 plus 1 over 4. I get 3.75, which I would prefer to write down as 15/4. And now we know the exact area under x cubed on the interval from 1 to 2.